Now in 10.2, we'll be dealing with almost the same what we have covered in 10.1, but we extend the concept in the three-dimensional space. So it's not only the xy coordinate, now it's x, y, and z. So this is the three-dimensional space. This is the x-axis, y-axis, and this is the z-axis. This is all the coordinate axis in the three-dimensional space. So any point here in general, it's just like we write it as A, B, C. So just like triple. It's not only order pair, it has like three components, A, B, C. Now just usually, how do we see the XY coordinates? So if you have like your right hand, just you're moving your hand towards the positive x-axis. Okay, so this is the positive x-axis. If you're just starting your right hand towards the positive x-axis, and you curl your fingers toward the positive y-axis. So this is the positive y-axis. This is where you curled your fingers. Then the thumb direction will be always towards the positive z-axis. Okay, this is what they call the right-handed rule. So this is the positive x. Your fingers, if you roll them, it's just like curl them toward the positive y-axis, and the thumb is toward the positive z-axis. Now, if we look at the three-dimensional space and we need to plot any point, usually with the two-dimensional space, you plot the points as you start with x and then y. So let's say I'm plotting the point -2, 5. So this is the x-axis. So this is -2, -1, -2 in the x-axis, and I need 5 in the y-axis. So you move toward the positive part. So this is like 1, 2, 3, 4, 5. So this is the point -2, 5. Now to represent the third coordinate, the z1, I need to move 4 steps upward. So this is up 4 units. So you imagine that you're drawing a parallel line to the z-axis. So this is 1, 2, 3, 4. So this is the point. So just like you're doing the intersection of the three lines, one in the x, y, and then you go up or down in the z-axis. So this is the point x, y, z. Same thing, let's check another point. If I need to plot 3, 3, -2. So I start with the x-axis, the positive 1, 3. So this is 1, 2, 3. This is the line. I'll draw a horizontal line. And then I need from y at 3. So I go to 1, 2, 3. So this is at y. And in z, it's -2. So I need to go 2 steps down, parallel to the z-axis. So 2 steps down, this is the point. So you just like you try to imagine it in the three-dimensional space. Now here it's showing how to plot the point and showing you the result as a cuboid. You see the result is just how did we move that x, then y, then up at z. This is the point. Now we've tried just to deal with the three-dimensional space exactly like what we've done with the two-dimensional space, but we'll add z, that's all. So if I need to find the magnitude of the vector or the distance between any 2 points in the three-dimensional space, remember always if we just have 2 points anywhere, if I have, let's say, this point and this point, if I need to find this line segment, I could call it the magnitude if I'm representing a vectors. I could call it the distance between these 2 points, okay? So I could use the word magnitude, length, distance. They are all the same thing, representing the same line segment. So if I need to find the length or the distance between these 2 points, it will be same as the magnitude before. So it's square root of delta x squared, delta y squared, delta z squared. So I'm having 2 points. One point as x1, y1, z1. For sure, this is in the three-dimensional space. And another point as x2, y2, z2. So the distance between them, or the length of this line segment, let's call this point A, this point is B. So the length of the line AB is the square root of delta x squared plus delta y squared plus delta z squared. Now this is a question for the same thing. I need just to find the distance between the points 1, -3, 5. Notice this is a point, not a vector. 5, 2, -3. So this is x1, this is y1, this is z1. And this point is x2, y2, z2. So the rule says what? How do we find the distance between these 2 points? So it's the square root of delta x, square root of delta x. See what's delta x? I'm changing the x. 5 minus 1 squared. So it's 5 minus 1 squared plus delta y. So if you start with 2, so we're doing y2 minus y1. So 2 minus 3, so it's 2 plus 3 squared. Same thing for z, so it's -3, -5 squared. So if you just calculate this, it will be equals to radical, I guess, 105. 105. It's radical 105. So just like simple distance formula. Simple distance formula. Okay, good, easy. Now again, just exactly what we've done before. There's something we call the position vector, where the initial point is at the origin and the terminal point anywhere in the three-dimensional space. So this vector, this is the 0 vector. This is a point A1, A2, A3. So this vector, we call it A1, A2, A3. Notice the notation. Here I'm using the vector notation. Exactly what we've covered before, but just we add Z. Now the magnitude, I have the vector. You see this is the vector A1, A2, A3. So the magnitude will be equals to what? A1 squared plus A2 squared plus A3 squared. So first component squared plus second component squared plus third component squared. Exactly as before. Now what if I don't have the question as a position vector? It's not ready as position vector. So I have the 2 points, initial point, terminal point. So if I have initial point, terminal point, exactly as what we've done before. So I need to subtract terminal minus initial point. It's always terminal minus initial. So B2 minus A1, B1 minus A1, B2 minus A2, B3 minus A3. Just directly, terminal minus initial. Now for the operations, the arithmetic of the vectors, just as before. So if I need to add 2 vectors, subtract 2 vectors, I'll add each component with its, the first component with the first, second with the second, third with the third. Same with subtraction, scalar multiplication. And again, notice that all of these arithmetic, the new result is again another vector. So we're dealing with a 3-dimensional space. The result will be a new vector in the 3-dimensional space. Just exactly the same thing. 0 vector, so it's 0, 0, 0. The additive inverse, it's -a, just like you multiply by -1. This slide is exactly the same. The only difference here is just only this. Instead of V2, we wrote V3. It's in the 3-dimensional space. It's exactly what we covered in 10.1, sorry. Now, once we're done with these vectors, another way to represent the vectors, as we did in 10.1 in the 2-dimensional space, we can use I and J, but this time for the third component or the third axis Z, we'll use K. So now we have I, J, and K. I, J, and K. I for X, J for Y, and K for Z. So the new one for I, it's 1. It's not only now 1, 0. It's 1, 0, 0. J is 0, 1, 0. And K is 0, 0, 1. So just like X, Y, Z. I is for X. It's 1. The rest are zeros. J for Y, it's 1. The rest are zeros. K for Z equals to 1. The rest are zeros. So any vector can be written as A1I plus A2J plus A3K. Again, these vectors I, J, K are unit vectors. If I need to do normalization, just same idea. I divide the vector by its magnitude. I'll get a new unit vector. We call it as u. Now see this question. This is example 2.3. It says we need to find a unit vector in the same direction as this vector, 1, negative 2, 3. Let's call it A. 1, negative 2, 3. Okay, so we need to find a unit vector in the same direction as this. And then write this vector A as the product of its magnitude and a unit vector. So we need to write the vector A as a multiplication of its magnitude times a unit vector, which is u. Okay, so it's easy. We know that u is equal to what? A divided by its magnitude. Okay, so let's try to find it. So this is equals to A is 1, negative 2, 3. Its magnitude, remember, we find it by what? First component squared, 1, plus second component squared, 4, plus third component squared, 9, and this is equals 1, negative 2, 3 divided by square root of 14. This is a scalar, so I can distribute. So this is 1 over radical 14, negative 2 over radical 14, 3 over radical 14. Now, this is the first part of the question. Find a unit vector, which we called as u. So u is equal A divided by its magnitude. This is u. Now, the second part of the question, they need us to write this vector A as the product. Remember, it's a multiplication times the product of its magnitude and the unit vector. So I need just to do this way. So I need to write the vector as A equals, from this equation, the magnitude of A times u. Okay, this is u. And this is the magnitude, radical 14. So A is 1, negative 2, 3, equals to the magnitude of A. We already calculated as radical 14 times u, the unit vector in the same direction, which is this one, times 1 over radical 14, negative 2 over radical 14, 3 over radical 14. So we wrote it in the format that they asked for. Okay, this format. If you need to check your solution, multiply by radical 14, you get back the same original vector A. Okay, so we wrote it in this format, just as required. Okay, what else do we have? Okay, this is a nice part of this section. We need just to try in the 3-dimensional space, just we can have any 3D shape. So we need to try to find an equation of, basically we'll use sphere for this part. We need to find the equation of the sphere of radius r with the center of ABC. Okay, how can we represent the sphere in the 3-dimensional space? If you think about the sphere or even a circle, let's just think about it in the 2-dimensional space first. If you have any circle, so the distance from, remember what makes any circle unique? Center and radius, center and radius. So always the distance from the center to any point on the circle is equal to what? The radius. So it's fixed distance. Wherever you take it, from any location, any place on the circle, the surface of the circle, it's all r. So if I find the distance between the center or any point on the circle, let's say any point on the circle is xy, and the center, call it AB, let's say. So if I find the distance from AB to xy, it will be always equals to r. It's always equals to r. This is the concept of a circle. Now we need to extend the same idea, but for what? For the sphere in the 3-dimensional space. So think if you have a sphere. Okay, let's say that this is a sphere in the 3-dimensional space. okay? And this is the center of this sphere. If you have the center as A, B, C, this is the center. And any point on the surface of the sphere, I can call it any point in general, it's X, Y, Z. And the center is A, B, C. The distance between the center and any point on the surface is equal to R, the radius. So same idea. So basically what I'm finding is just exactly the same idea like the distance. So the radius, which is the distance between these 2 points, equals the square root. Remember, what do we do? Delta x squared, delta y squared, delta z squared. So this is x minus a squared plus y minus b squared plus z minus c squared. Just to make it look nicely, I can square both sides. So r squared equals x minus a squared plus y minus b squared plus z minus c squared. And this is the equation of the sphere. This is the sphere equation. Okay, so this is the sphere equation with center of ABC and radius R. This is the sphere equation. Okay, so basically what we're doing here in this question, we're trying just to use the distance idea, okay, the distance idea to find the equation of the sphere. Since we know that the distance is always R, it's always fixed between the center and any point on the surface of the sphere. Now the last question we have here, you see this is the sphere in the 3-dimensional space. They show you that the distance between any point and its surface is always R. And how do we find the equation? Just by using the distance formula between these 2 points. Now the last question here is this one. This is the opposite, okay? I have the equation, okay, and I need to find its represent which shape. I have the equation but extended form, okay? So just this is the form of the sphere equation. So they expanded, so it's written like quadratic of x, quadratic of y, quadratic of z, and I need just to write it as a 3D shape, which we don't know yet it's equals to what. So looking at this equation, I have a quadratic form of x, quadratic form of y, quadratic form of z, and a constant term. So I'm expecting this one to be maybe a sphere. Let's see. The only way to solve this question is by completing the square. So this can be done by completing the square. Okay, how can we complete the square? Remember, how do we complete the square? I need just to move all constants to the other side. Do we have any constant? Yeah, I have this one. I'll move it to the other side. So it will be negative 36. Try to rearrange. Just take x's together. So I have x squared minus 4x. So I took x's together. Now take the y together. So I'm having y squared plus 8y. Same for z. So we have z squared minus 10z. Now what we'll be doing is completing the square for each one of them. Remember, how do we complete the square? We usually add and subtract b over 2 squared. You add it and you subtract it. Plus minus, so we still have the same value. So either we have two choices. Remember, when you deal with equations, so let's say that the equation a equals to b. So if I need just to make plus minus a value, I'm allowed to do what in the equation? I can add plus c minus c. So still the same equation, it's valid, a equals to b. What else I can do? I can add c to both sides. So I can say plus c and there plus c. So still the same equation. So it's up to you. Usually for completing the square, either you add and subtract in one side or you add for both sides. Both of them are fine. It's up to you in the end. Okay. So now I'll try just to add both sides. So for the first one, for the first x part. What's b over 2? b, remember, b is the coefficient for x. So b here is negative 4 divided by 2 squared. So this is equals to 4. That means I need to add 4 here. Okay. And add the same to the other side. Minus 36 plus 4. Let's make some space for the coming terms. So this is x squared minus 4x. We said plus 4, and I added 4 in both sides here and there. Again, you could do plus minus to the same side. Now let's move to y. So b is 8. 8 over 2 squared is equal to 16. So I need to add 16. 8y plus 16. There I'll do plus 16. Same thing, same technique to z. So this is z squared minus 10z. b is 10, negative 10, divided by 2, 5, squared 25. So I need to add 25 both sides. 25, 25. Now all of these, each one of these, the three, are perfect square. These are perfect squared. How can we write them this way? So x, remember, we take the square root of the first, square root of the last, okay, and we take the sign always from the middle term, only the sign. It's negative, and this is all squared. So square root of the first, square root of the last, and the sign we use the middle one, all of it squared. Now for the second one. So it's y, 16 is 4, sign from the middle is positive, all of it squared. Same with z. Square root of the first, square root of the last, sign from the middle term, all of it squared. And this is equals, we need to add up this. So this is 20 plus 25, 45 minus 36, it's 9. So this is clearly an equation of sphere. This is sphere equation. This is a sphere with radius equals to 3 and center. The center always the coefficient. Remember, the rule in general is x minus, y minus. So the center will be for this one same. If it's negative, use the same value here as 2. Plus 4, so you use negative 4. Negative 5, I'll use 5. So this is an equation of a sphere with radius 3, which I get from here. 9 is 3 squared. Radius 3 and the center is 2, negative 4, 5. Okay? So for this style of questions, if it's like 3 quadratic equations, x, y, z, we do completing the square for each one of them. And the result here is a sphere equation. And that's all about section A 10.2. So it speaks exactly almost same like 10.1, but we extend the concept into the 3-dimensional space. So instead of only x, y, we have x, y, z. Hopefully you enjoyed the sections 10.1, 10.2, and next time, inshallah, in the class, we'll move to 10.3. Take care. Bye-bye.